Good evening, everyone, and thank you for attending our webinar this evening, ACM Chicago, IEEE Computer Society Chicago, and we also have ACM DC Chapter 2 as well on this call. So thank you all for attending this evening, and hoping you're having a wonderful day today. So tonight, for our July presentation, we are going to have Nikhita Sharma from Veil Systems, and it's a Chicago-based company, and she will be talking about automatic speech recognition and overview. So first of all, welcome to the ACM DC chapter, and Terry Grosheim, who is the chair. Terry, go ahead and mention a little bit about the ACM DC chapter.
Sure, thanks, Alvin. I'm actually a co-organizer along with Andrew Conklin. I relocated to DC from Chicago about a year ago and have become a more active co-organizer and trying to resurrect some meetings. So thanks, Alvin, for having the DC chapter and inviting us today. A little bit about our chapter. We're actually a meetup group. There's a branding situation. So we're actually a meetup group of approximately 14,000 professionals that meet regularly to discuss diverse topics in computer science. Our purpose is to bring computing researchers, entrepreneurs, and practitioners together to address the field's challenges. So keep an eye on our meetup site. That's the best way to see what the DC chapter is up to. And if you have any ideas or want to participate in our group, please feel free to reach out to me through the meetup site or after the meeting today. Thanks, Alvin.
All right, thank you. Yeah, thank you, Terry, and thank you for the ACM DC chapter to be here with us this evening. And hopefully we can have more collaboration on similar type of meetings and webinars as well. We also want to welcome those from IEEE Computer Society Chicago, our sister chapter. We have been doing this with ACM Chicago pretty much, for the past, 2 years or so, because they're similar topics. So those who are not familiar, IEEE is kind of similar to ACM. It's another type of organization, computer organization. And we are the Chicago chapter for the Computer Society. And so we have had meetings with ACM Chicago pretty much almost every month. So I'm the chair of this, and our vice chair is Gina Martinez. And, we have our web, Facebook, our social media links there. And we also have our YouTube channel, so you can see our previous webinars and meetings that are recorded there. And if you want to become an IEEE Computer Society member, you can go to computer.org/membership/join. You can get, discounts or so to IEEE Computer Society conferences. And these slides will be made available to everybody who has joined or has registered this evening. So you'll get a copy of these slides. And of course, ACM Chicago, the main sponsor here for this evening. So those who are not familiar with ACM, ACM is the Association for Computing Machinery. We are the Chicago chapter. We normally do these at Loyola University at the Water Tower in downtown. We did do the past 2 meetings in June and in May, actually at the Lakeshore campus. And we did a hybrid there, and that was our first that we did the hybrid, since the pandemic. So hopefully we can do a little bit more hybrid later in the fall. We will see. But hopefully we can do that. So I'm the chair for ACM Chicago. Vice chair, you can see on the line in our panelist is Mark Temkin. Our treasurer is Greg Newmark, who unfortunately could not be here this evening. And a lot of you probably knew about this particular event from our meetup group, maybe also as well from our social media links too as well. We also have our YouTube channel, bit.ly/ACM Kai video, so you can see all our previous ACM Chicago webinars if you've missed any, and you can subscribe so you can get the latest ones. And if you want to become an ACM member, you can go to acm.org/membership. All right, so the reason why you're all here today, this evening, is for tonight's presentation. So I will now hand it over to Mark to present our speaker.
I'm really looking forward to this talk tonight. I think that having come from the music side, the whole aspect of communicating with a computer not through a keyboard is very interesting. And so I think this will be a great talk tonight. Our speaker, Nikhita Sharma, works for Veil Systems, and she's had numerous years of experience with machine learning and focusing on conversational AI along with automatic speech recognition, which is what this talk is about. And among her, in her educational background, she has a master's in computer science from Iowa State University. And so let's have a big round of Zoom applause for our speaker, Nikhita Sharma.
All right, thanks all for joining, and thanks for having me and giving me the opportunity to talk with you all today. I'm going to be presenting on automatic speech recognition, and I'm going to give you a high-level overview of speech recognition, how does it work, what's the history of this technology, and also go through some of the models and algorithms that are used very popularly in this space. We will also look at evaluating these systems and the challenges that exist for them today. So to start off, for those who are not familiar with ASR systems, ASR system is an engine that transforms human speech into readable text or a transcript. ASR systems are very popular these days, and especially recently have been very popular on these social media platforms like TikTok and Instagram for real-time captions of reels and videos. Spotify also uses it for podcast transcriptions, and of course, Zoom and other technologies use it for meeting transcriptions. So you can convert the speech to text, but you can do more with the text than we just talked about. The transcripts from an ASR system can be used for many other use cases. For example, in natural language processing, you can use the text to do intent determination, which is trying to figure out what the user is trying to say given the speech. So you convert the speech to text, then you use the text to determine the intent, and then you understand what to say back to the user if you are in a conversational agent or something like that. So you can do other tasks with the transcript. You can perform sentiment extraction. You can do, of course, language translation, and you can also do video and audio captioning. You can use it for dictation systems, and you might have used it on your own personal computers. If you're feeling too lazy to type, you can just speak, and the system will transcribe everything you said. So, of course, there are various areas where you can use ASR systems. So let's look at the history a bit over here. So speech recognition has seen a lot of growth over the past decade, and that's mostly because of the advancement in machine learning. So if you think about it, speech recognition is an integral part of natural language understanding. So the goal is to have machines, to give machines the ability to analyze and process and generate languages. And the attempts to do so have been going on for hundreds of years. So most people think that speech recognition and natural language understanding started with Alan Turing and the Turing test, but there's more to it. And I'll give you an overview of that history. So it all started in the 13th century, which is a very long time ago, when Jewish Kabbalists, they played around with the letters of the Hebrew alphabet to produce and generate text. And the idea behind this was that they wanted to see if they could combine letters and produce new sentences, they could, learn things that they did not know before. And, this would reveal some kind of wisdom that they are not aware of. So their intentions behind it was to gain, more knowledge beyond what was available. And similarly, there were mystics who played around with the symbols of God. and they wanted to see if they can learn more about their deity by just generating these new combinations of letters and sentences. So at one point, this was even considered dangerous because the religious people thought that you can get to know so much more just by playing around with language and symbols, and you might profess some knowledge that you're not supposed to have. So there was a bit of a bad side to this early on, and after that, inspired by all these combinations, the science of combining letters, the German polymath Leibniz, he imagined a machine which is called the great instrument, which he called the great instrument of reason. So he was inspired by the idea that you could model certain symbols and alphabets and generate new sentences. So he applied this to the idea of generating new thoughts. So according to him, if you could have an alphabet of human thoughts, and you could have a list of logical rules in which you can combine them, you could create a machine that would apply those rules and create new thoughts. And it would solve all disputes that mankind would have. So he famously said that when there are disputes among persons, we can simply say, let us calculate. And though you can just press a button on the machine, and then it will give you an answer whether who is right in that debate. So moving forward, this is more of a formal approach. So Andrei Markov and Claude Shannon introduced the statistical approaches into language modeling. So Markov brought the idea of probability theory and causality into this field. And according to him, the chance that a certain letter appears in the text is dependent on the letters that appear before it. So Shannon built a statistical framework for the English language and explored all this correlation between words and letters. So on the right, you can see an example of the initial experiments done by Shannon. So he started off with all the 26 letters of the English alphabet and a space, so 27 letters. And he started playing around with them and picking some up randomly. And this is the initial text that he came up with. And then as he started playing around with the probability theory more, and he developed a more complex model where he picked the words instead of letters and took into account the probability with which a certain word appears given the context, he was able to come up with something like the second paragraph, which is more close to how the English language is and resembles real sentences. So this gave the idea of the connection between words and letters. It gave it some kind of movement over there. So after that, we come to the history of natural language understanding, which people think was started by Alan Turing. So this is the more familiar side of things. And Alan Turing imagined a smart machine that could interact fluently with humans via a typed text on a screen. So the Turing test is very famous, and in which you have three players, A, B, and C, and where C is the interrogator. And the idea is that the interrogator interacts with written responses on a screen, and they have to be able to differentiate between the players A and B just based on that text input, if it's a human or if it's a machine. So this theory or this Turing test was actually brought into action by the first chatbot, which is called ELIZA. So ELIZA was the first chatbot created by Joseph Weizenbaum, who was a computer scientist at MIT's AI lab. So ELIZA, although this is not, this is conversational agent, it did not use speech recognition at that time. It was just purely text-based, but it really showed that some kind of interaction between the humans and computers. And ELIZA was very limited, and it was just based off of pattern matching and substitution methods to give the user a response. But the interesting thing is that Weizenbaum ensured to design ELIZA in such a way that it was based on these techniques, which is used in psychology, where you can just repeat what the person said and then add a little bit of something to it, so that it gives a sense of that. It gives a sense that the machine can understand you. So it was fairly limited, but ELIZA was put on personal computers, and humans found it very engaging. So much so that Weizenbaum's assistant would ask some privacy while speaking to ELIZA, because she thought that the machine could understand it, even though she knew how it operated. So it just shows that how superficial these interactions were at that given time. But by today's standards, ELIZA it will fail very quickly, and you can understand that it is very limited if you ask it a few questions. And there's in fact a website which you can go to, and you can play around with the ELIZA in its current form, which is still limited, but it's interesting to look at. And recently, ELIZA became popular again because it was referenced in one of the episodes from a TV show called Young Sheldon. So here I'm going to play a snippet of Sheldon's interaction with ELIZA. This is when he brought a new computer, and you can have a listen to this.
Hello, I am ELIZA. My parents are fighting a lot. I see. Can you elaborate on that? My mother bought me this computer, but my dad says we can't afford it. Do you have issues with your mother? No. She makes me spaghetti with hot dogs cut up in it. Can you elaborate on that? Are you going to help me or not? Hello, I am ELIZA. The future might be overrated.
All right, so as you can see, Sheldon got frustrated with ELIZA very quickly because it was very limited. But this is an example of what an interaction with ELIZA looked like. So this brings up a question about why is speech recognition so hard? So speech recognition is hard because there are multiple sources of variability in audio files. So it can depend upon the style of speech. So if you're having a conversational speech versus if you're reading something which is already written down, there can be variations in that, in the way that the speed in which you talk or the way that in which you enunciate can be different in a informal conversation versus read speech. Similarly, if you have isolated words or shorter commands, it was easy for an ASR system to understand that versus continuous speech, which has more variability. So there are also other factors such as accents and the speed of talking, the gender, which is all based on the speaker themselves. So all of them also add variability. Speech recognition can also be affected by the background noise. So if you are in a very quiet environment, versus if you are in a noisy environment, that can impact speech recognition. And one thing that really is like a roadblock for speech recognition, which used to be a roadblock earlier, was that if there are multiple people talking in the background, it can mess up your transcripts. But there are ways to deal with that, which you can read up on. But that's also another factor that causes variability. Also scope. So if you have a general speech model, which with a very large vocabulary, the user can probably say anything they want. That's obviously harder than a domain-specific model in which your vocabulary is restricted and there are only a certain set of words that the user can say. So all of this makes it very hard for machines to understand speech. But now let's have a look at how ASR systems actually work. All right, so in a traditional ASR system, you have 4 components. The first one is the lexicon. Second one is acoustic model. You also have a language model and a decoder. So whenever audio data comes in, it is passed to this decoder module, which uses all these 3 components and gives you the most likely word spoken as an output. So if you were to train your own ASR system, you would have to have some kind of training data which can, with certain labels. So the training data usually looks like audio data and the corresponding human transcripts. So once you have that, you can train your own ASR system using the following methods that will be discussed further. But this is a very overall, this is a very high level overview of how ASR systems work, and I'm removing a lot of the complexity from it, but just take it with a grain of salt. So the first step in speech recognition is to convert the sounds that humans create, which is an analog signal, into a digital format. So you can do this using a microphone. A microphone already does that for you. So you have the time domain waveform, and you get a spectrogram when you use a microphone. So this has information about the frequency and the time, and it also has the intensity mapped with the colors. So in this heat map, you can see that the more the intensity, the darker the colors. So this is how you convert the analog signal into a digital format. And then once you have that, you need to feed this into the ASR system. And the ASR system cannot work on that spectrogram itself. There is a feature extraction done after this. And the reason being that we want to focus on what matters most in that audio signal. So we extract features from it to represent 2 things. One is the content of the audio, and the second is the way the speaker is saying that. So there might be differences in the way, depending on the speaker characteristics, they might pronounce things differently. So all that information needs to be captured. So you can use MFCC features and CMVN features in order to do feature extraction. MFCCs are widely used, and they stand for mel frequency septal coefficient. And once you normalize them, you can call them CMVN. And you can also use I vectors, which represent the speaker information. So once you have that, you can move forward with your ASR training. So another question is how this audio signal gets converted to the features. How do you even create discrete units in this? So typically a siding window of 25 milliseconds is used, and it is 10 milliseconds apart. And each window is called an acoustic frame. And then you extract features for each acoustic frame and for the whole audio wave file. So the reason why 25 milliseconds is used is because it ensures that there's enough signal in that audio frame, and still it can generalize across different speakers. So with a lot of research, people came up with this 25 millisecond window. So once you have the features, you can rethink the speech recognition problem in a different way. So if you have X, which are the acoustic features, you want to predict W star, which is the most likely word sequence. And W can be any of the possible word sequences. So this is called the equation of statistical speech recognition. And the idea is that you are trying to guess the most likely word sequence given all the words that you know and given certain features of the acoustic form. So if you apply Bayes' theorem to this, you can divide this as an acoustic model and language model. And the acoustic model is basically the probability that you see a feature given the word, and the language model is just the probability of the word itself. So let's look at the acoustic model and language model in more detail. So the acoustic model typically deals with the raw audio format. You get the audio waveform, you convert it to the features, and then you try to map those features into the words that they correspond to. So that mapping comes from the acoustic model, and the language model tries to make sense of that, and it helps the acoustic model make more natural sentences, and it tries to correct the grammar of that sentence and also disregards predictions which might not be probable given your data set. So in speech recognition, you would think that we would train on those acoustic features and get the words directly. That is also a way to train them, but we'll talk about that in more detail later. But typically in a traditional ASR system, you do not predict the words directly because this would require a lot of training data to do that. And also if you have, say, 100,000 word vocabulary, it will be too many classes to train the acoustic model on. So instead, words are represented as a sequence of phonemes. And if you're familiar with phonemes, if you've worked with anything in NLP, but a phoneme is a distinct unit of sound in any spoken language that distinguishes one word from another. And for example, if you have the word cat and the word bat, they only have one phoneme which distinguishes the words from each other. So there are 44 phonemes in the English language, and there are a few examples here. For example, ways is represented like this. So these can also be considered the way you pronounce the word itself. So you must be thinking, how can we know how can pronounce each word that exists in the English language? So luckily, we have all this work done for us already. And there are pronunciation lexicons, which are available in the form of dictionaries. And you can directly download these. And these are created by experts in the language. And so you can have a one-to-one mapping for each word and the corresponding phonemes that make up the word. So this is called the lexicon, and the lexicon is one of the components of the ASR system. So the way that the lexicon is represented in the system is using a Markov chain. So for example, if you have a word called word 6, you can represent it in the form of a Markov chain. And there are self loops over here which help you model the time variance in the pronunciation, because some people might pronounce 6 differently than others. So all of that is captured in this Markov chain as well. So this is what we want to see as the output from your ASR system, but we'll talk about it further. So the acoustic model comprises of, the role of the acoustic model is to convert these acoustic features into context-dependent phonemes. So the acoustic model can be considered like a black box in which you get a sequence of acoustic features and you have to output a sequence of phonemes. And we are talking about a sequence of phonemes because we are talking about this with respect to continuous speech. So that's why it has to be like a sequence instead of just isolated words. So traditionally, people would model the acoustic model using hidden Markov model. So this is because they have a good search algorithm for, you can use dynamic programming and you can search throughout that graph once it's ready. And you can consider the HMM model for acoustic modeling as a big graph with weights on it. It will become more clear as we talk about it. So you can also use neural networks to learn this mapping between the features and the phones. Because of the popularity of deep learning, people started using neural networks to train ASR systems as well. And that also led to an increase in the overall accuracy of the models. So if you look at this more deeply, you'll see that on the left you have acoustic frames and the features corresponding to each frame. And we are trying to map this to this, the lexicon or the phoneme breakdown of a word. Here it represents the word 9. So the transition between all these phones and the corresponding observables, which is the features, can be modeled using the hidden Markov model, and the distribution between the acoustic features for each phone can be learned through a Gaussian mixture model. So the probability between this phone and the acoustic features is learned using the GMM. You could also learn this using the neural networks. And by learn, I mean you can train a model to learn that probability distribution. So this way you can have two different type of architectures. So you can have an HMM GMM model, or you can also have a hybrid HMM neural network model. But the goal over here is the same. You have, you're trying to map acoustic features to phonemes, and you can do that. You can represent the phonemes using Markov chains, and you can map the features to phonemes using either a Gaussian mixture model or a neural network. The difference here is that the Gaussian mixture model focuses on getting the likelihood that if you have a given phoneme state, what is the likelihood of seeing a particular acoustic feature? Versus the neural network is based on the posterior probabilities. So it tries to map that and directly get a relationship between the features and the phonemes. So that's why this probability of X given the word and versus probability of the state given the feature. That's the difference between these two architectures. So once you have the acoustic model and the lexicon, you can imagine that you can use that to convert the features into the phonemes, and you can convert the phonemes into words using the lexicon, the one-on-one mapping. The next step is to make sentences out of this, and that is where the language model comes into place. So the language model calculates the likelihood of a sequence of words. So it predicts one word given all the words that it has seen before, and whatever vocabulary you have for your model is very important here, because the language model is only trained on the human transcripts that you have for your data set. So the language model helps you make a decision. If the acoustic model comes back with certain phonemes, it can help decide which is more probable than the other. For example, it can help us distinguish between recognized speech versus recognize speech. Obviously, one is more probable than the other, and this is modeled in the language model. So the way language models work is that you can have a count of the words, how many times a word or an n-gram appears in your training corpus, and this way you can train either a unigram model, bigram model, and so on. And typically, the n-gram is usually a 4-gram for most of the models, because as you keep increasing that number, your model becomes more complex, and it takes longer for you to train it and to get the results from it. So if you have a unigram-based language model, it will only look at each word independently. If you have a bigram model, it's going to look at one word, the pairs of words, instead of just looking at one word. So for example, if you have a sentence like simplicity is the ultimate sophistication, if you had a bigram model, the way you would calculate the probability of the sentence would be the probability of simplicity, then the probability of is
given simplicity, then the probability of the given is, and so on. So you can see how we can come up with a language model in this way. There are also pre-trained language models. So because you have so many corpus of text, you can model all these dependencies between the words and the n-grams based on other text corpuses as well. So you can have pre-trained models that can be downloaded, and you don't have to do your training just to generate the language model. So overall, once we have all these components, this is how the decoding works. So you have your audio features, your audio waveform, you extract the features, then you use your acoustic model to convert the features into phonemes, and then you use the lexicon to convert the phonemes into words, and then use the language model to build out the complete sentence. So that's how decoding works in traditional ASR systems. You could also have a different approach of training these, which is an ongoing research area, and there have been multiple papers about this topic, which is called end-to-end speech recognition. So in end-to-end speech recognition, you do not care about the phonemes or the mapping between them. You just directly map a sequence of input acoustic features into a sequence of words. So you don't even need a language model, but having a language model obviously improves the results because of the reasons mentioned before. But the approach here is to just have an encoder and a decoder. So the encoder will encode your features into something called like a context C, which can be like context C. And then the context gets decoded into a sequence of words using the decoder. So it's a cleaner approach, and it would probably make fewer errors because you don't have to deal with the uncertainty of getting the correct phoneme, and you can just directly map your features to words. But of course, you will need a lot of data in order to train this kind of model, and there is no, there's a lot of data for speech recognition available. As long as you can get it transcribed, you can train a very big model using this technique. So now let's look at how these systems are evaluated and take a look at some of the popular speech recognizers that are used. Right, so to evaluate these kind of systems, there's a metric called word error rate, which is used. So word error rate compares the predicted output, let's call it the hypothesis, to the human transcript or the reference. It is a word-by-word comparison, and it's based on Levenshtein distance, which is Levenshtein distance between two sequences is the minimum number of edits you need to make to change one sequence to the other. And of course, the type of errors that you can make would be insertions, deletions, and substitutions. So for example, if you have a human transcript which says the dog is under the table, and the ASR system predicted the dog is the fable, because these are very similar sounding, these kind of errors can happen. And in order to calculate the word error rate, you have one deletion over here and one substitution. So it would be 0.33. And so you got 1/3 of the words wrong over here. But obviously, there are disadvantages to using this because you do not get details about, what if there was a substitution error, was it a big substitution error? Did it replace the word, all the characters in the word, or is it like a smaller error? You don't get that kind of information. For example, if you have a reference called, say, I want to pay my bill, and the ASR comes back with, I want to say my bill, you still might be able to make sense of this because, the word bill has been replaced, the word pay has been replaced by say. So it's just different by one character and one word. You also miss out on information of whether the system did not transcribe a keyword properly. Because if you cannot transcribe I want to, and if you get just pay my bill, it still makes sense, versus if you just get I want to bill, that doesn't make sense at all. So word error rate is not the best way to evaluate these systems. It depends on your use case, on how you want to use these transcripts, and you have to come up with other evaluation measures as well. So here's a look at some of the popular ASR systems that are used. Some of the open source ASR systems are these pre-trained speech recognition models. LibreSpeech, Zami Speech, and Deep Speech are very commonly used in academic papers. You can also build your own ASR model using these open source toolkits like Quality and HTK Toolkit. Quality is, I've worked with Quality a little bit, and you can train domain-specific models using these toolkits, which can perform better on your data sets versus just a general model, which might not be giving you the results you want. So pre-trained models have lower accuracy, and they are free. So there's like a trade-off that you need to make over there. But if you choose to build a custom model using your own training data set, there are certain advantages to it. Like you can make the model very resilient to the background noise if you know what kind of noise to expect. And similarly, you can train it to recognize domain-specific words, which might not be present in other general models. So other ASR systems which are very common are these commercial ASR systems like Google Speech-to-Text, Speechmatics, Amazon Transcribe, etc. Of course, they train on a lot of data and have easy-to-use APIs, so they have the best word error rates. But of course, they are not free, and you have to pay some kind of money to get each transcript. And there's also lack of control over the system, so you can't make very frequent changes to it. And that's the disadvantage of using these, although you get good accuracy from them. So given all this, there's still some challenges for ASRs today. Although we have achieved human like word error rate levels, some of these commercial ASRs are very accurate, but still there's a lot of work to be done. They might not work for speakers from different countries, and because there are still so many differences in the way that we speak, and because these models are trained on data sets from certain countries, they might not be applicable, or they might not work well for people from other countries, etc. There are also there's less models available for different languages. Like even for like a language like Hindi, there are not a lot of speech recognition models available. So these are things that can be worked on in the future. There are also privacy concerns because some of these large companies train on very big amount of data, and then they also get the data from without permission from the users. So of course it can contain PII information, and if you have unencrypted audio video files saved, that can also raise concerns about privacy, etc. So hopefully I got you a bit curious about the speech recognition and give you an idea, general idea of how it works. And if you would like to play around with it, it would be good if you could incorporate it in some of your use cases using the open source APIs, or even build your own ASR model if you feel up for it. And with that, I'd like to open it for questions.
All right, thank you, Nikhita, for that wonderful talk. So we have time for some questions. So if you have a question, please type it in the Q&A that you see in your Zoom, and we'll address those questions. And Mark will do the moderation of our Q&A.
Right, and in the meantime, I've got a question to start off all the questions, and hopefully that will inspire the rest of you to ask your own questions. So English is famous, I think, more than many other languages. I did take Spanish, so I might be on shaky ground here, but English is famous for a lot of words that sound the same. And of course, they have different spellings, and of course, they have different contexts. Now, some of those are, pretty exclusive. I was thinking before, like the lion has a mane, M-A-N-E, or I'm going to Main Street, M-A-I-N. But even one of the words that I saw in your presentation, bill, B-I-L-L, that we typically think that's an invoice, something financial. But if it was a government context, then it would be referring to a law. And of course, if it would be referring to some of our guests here, that would be their first name. So does ASR try to address that kind of that sound-alike issue with English words?
Yeah, sure. So like I said, the language model is the part of the ASR that deals with this. So if you were to say the lion has a mane, the probability of mane would depend on the context. So that's how speech recognition deals with those kind of issues. And so you can have similar sounding words, but you can distinguish between them if you have a good language model.
Great. Okay, so our first question is from Roberto. What's the range of computing power needed for ASR? Or more specifically, how small a system can be used? Can it be a RPI, an Arduino? And besides CPU speed, how much memory is needed? So big question.
That's a good question. So it depends on the model that you're training. So if you were to train, say, from my experience, if you were to train like a model on 25 hours of audio data, and if you don't use a GPU, it could take you like 24 hours to train it on like a normal Mac. With regard to memory, it's usually not a memory intensive activity. Training these kind of models requires more CPU power than the memory. Like 2 GB of memory is sufficient to train, 2 GB of RAM is sufficient to train a 25-hour ASR model.
Great. From Pat, you mentioned removing background noise. Can methods such as fast Fourier transform be used in audio processing to isolate frequencies and segments of speech?
Yeah, so when we extract the audio features, the MFCC features that are used, they incorporate that already. And the reason that these features are popular is because they are able to capture what the user is saying and not focus on the background noise that much. So that is already incorporated.
Okay, and Neil wants to know, can you explain the linkages in training among the language model and the phoneme models?
The language model and the phoneme, sure. Let's look at the diagram again. All right, so this is what the decoding looks like. So when you have the phonemes that you get from the acoustic model, and you want to convert the sentence, so we use the pronunciation lexicon. So to convert each phonemes, so how do you even combine these to form words? So that comes from the pronunciation lexicon, and then the language model just changes if you got one word wrong, depending on the context. So if, like Mark mentioned, if you had something like the lion has a mane, and then you got M-A-I-N instead of M-A-N-E, the language model, because it knows the probability of that happening is different, it's going to change that back to M-A-N-E. So that's how acoustic model and language model work together to give you a good output.
Great. Harry wants to know the phoneme discussion reminds me of the secretaries of yore. days gone by, who took dictation with phonic symbols, and also the court reporters today. The worker recorded the sounds by hand or by machine, but then had to use their own knowledge or perceptions to reproduce the original words of the speaker.
Interesting.
Matthew's question is, how can you address speech recognition while someone is speaking as opposed to requiring the whole sequence before being input into the model?
Right. So this is, so there are multiple ways you could do speech recognition. One is like the online or streaming mode. So you get the audio file in chunks. So as the speaker talks more, you get more parts of the audio file. So this is called something, this just makes use of the left context. So if you had like a sentence that you're trying to decode, if you only have audio waveform till a certain point, you get the features for that and transcribe that as more audio keeps coming in. Versus if you have like an offline decoding in which you don't need real-time decoding, you can use both the left and right context in order to get good transcripts. So obviously there's like a little bit of a drop in the accuracy if you only use left context, but you could do both.
Okay, and Tim wants to know, he says, thanks for the great presentation. And just a quick question, what is the level of ASR usage now? How many world languages can be recognized by ASR?
Sure. So like big companies like Google, I think they have around 150 languages that they support in their APIs. But if you look at open source models, they're usually limited to English, Spanish, French, and German. Those are the ones that I've seen are most popular. But yeah, if you want to pay for it, you can support about 150 languages.
Similar question, but what is the state of affairs for ASR for other languages? And are there some languages where it is much easier than for English?
Sure. So the most difficult part, I would say, if you want to train this for a language which doesn't have that much data available, would be, of course, getting the audio as well as getting the corresponding transcript. So you need to transcribe it. And also you need the phoneme to word mapping. So if there's like a very less frequently used language, if you don't have domain experts who can give you that mapping, that's a problem. But if you have that, it's just a matter of having data transcribed by humans and then just training a system on that.
And again, from Neil, further to my question about the interactions between the language models and the phoneme models, is there feedback and training that adjusts the likelihood of a phoneme based on the probability of a particular word? In other words, if a phoneme is unlikely because no likely word that contains that phoneme is expected, does the training of the phoneme model take that into account?
So he's referring to the words, the probability of the word itself. Let me see if I can read his.
I guess what's
yeah, so
kind of like, what kind of sound are you, based on some particular word, are you expecting certain sounds, around it?
Sure. So I think from the way I understand it, he's trying to say, how do you align the sound and the phoneme? So that kind of alignment is done with model. And then in the end, you would ideally, if you train an ASR system, you would have a decoding graph, and that graph would have all the possible words and a probability associated with them. So this could possibly look like something over here on the right. So once you have that, all of these words sound very similar, but they have different probabilities of occurring. So that's how that's taken into account in the ASR system.
Great. Thanks for all these questions from the audience, and thanks for answering them. So that's the end of our question and answer period, and let's turn it back to our host, Alvin.
Yeah, thank you very much. So I have a poll here, so if you have a chance to, if you could go ahead and run this poll. so we have a better indication of how you learned about this meeting, also as well the quality of the webinar, how valuable webinar it was to you or your organization, and how we can be able to improve that. So this will really be helpful. So I'll keep it up there and return back to sharing my screen. All right, so yes, this pretty much ends for our kind of school year, I guess you may call it. We won't have one for August, so we will resume back in September. So we'll take a summer kind of break. But if you want to, look at other webinars that we've done in the past, go to our YouTube channel, which is listed there, subscribe, and you will see our previous ones. So like last month, we had one on Flutter. So you can also watch that too as well. And this particular recording will be made available after we process it. Probably give us about a week or so. We'll be able to post it on, and then we will send the email to all those who have registered for this webinar. So you'll receive the copy of the introduction slides, the video recording, and also the slides to this today's talk. And also as well, we are always looking for more volunteers for our ACM Chicago. It's us, the volunteers, that really continue to make this thriving. So if you are very interested, if you have skills in writing, planning, doing videography, audio editing, it's a great way to network with other future speakers and topics. And I think for a lot of people here, if you want to bring something back to the community with your expertise, this is a great way of doing so, and it doesn't require a lot of your time. So you can be able to, if you're concerned about in terms of your commitment, there's not too many hours that you need to kind of worry about to commit to this. And of course, we're looking for more speakers and topics. So if you want to give a talk to our ACM Chicago chapter, IEEE Computer Society Chicago, please let us know. You can contact myself, chair@chicagoacm.org, or Mark, our vice chair, at vicechair@chicagoacm.org. All right, so thank you very much all for attending. Enjoy the rest of your summer. Look for an email that will give you the recording and the presentations. And thank you all, and have a good evening.